So hi everyone, thanks for being here and this is joint work with Vipul Goyal and Amit Sahai from UCLA and Microsoft Research. So let me start by telling you what commitments are in general and what non-malleable commitments are. I'll not go into too many details unless somebody specifically asks for them. So consider the simple setting of auctions where there is a seller who has an item to sell and he wants to give it to the person who is willing to pay the highest for it. So there are all these people that make all their bids, and the purple guy here is willing to pay $250. So obviously the green guy wants to make the maximum profits, so he decides to give it to the purple gentleman. But now we'd like to design auctions that are optimal for the seller, which means that the seller should be able to get the maximal profits. Clearly in this situation, if everybody can see other people's bids and they are only allowed to bid once, the purple guy can have the following strategy. He just looks at everybody else's bids and bids at just one greater than the second highest value. For example, if he just says $201, the green guy loses the remaining $49. And therefore, it is important to have bids sealed in auctions. So this was a very simplified example, but in general in many auctions, it is assumed that the bids of people are a function of their own valuations and not a function of what other people also said. So, so it's important that everybody has an independent bid, and we'd like to do this securely over the internet instead of having to actually write it on paper and seal it and post it. So the cryptographic object that one could use here can be a commitment scheme. In a commitment scheme, a committer can lock his message inside a box and pass it on to a receiver, such that later on when the committer sends a key to open it, the receiver can open the box and check what the committer sent him before. Electronically or as a protocol, a commitment generates a transcript between a committer who has an input message M and a receiver based on some randomness, such that during the decommitment phase, the committer can actually reveal the message and randomness. And this scheme should have binding and hiding properties. For this talk, we will only be interested in statistical binding and computational hiding, which means that so the probability that the committer was able to open to another message if the decommitment is accepted is really small, and the transcript of the commitment, but not the decommitment, just the commitment, should not reveal the underlying message to the receiver. So for any polynomially bounded receiver, the transcripts of commitments to different messages should look indistinguishable. So so given such a commitment, it looks like everybody can just generate commitments to their bids and send it to the green guy, but that doesn't work, because this definition still doesn't rule out attacks where the purple adversarial guy could look at the commitment sent by someone else and generate a new commitment on his own that is somehow related to the commitment sent by the honest guy. So in particular, hiding doesn't guarantee this. Without even knowing what the other person's bid is, he could launch such an attack. So what solves this issue is our non-malleable commitments introduced by Dolev, Dwork and Naur, and let me tell you more about them. So I'll begin by telling you a little bit about the model. We don't assume any setup assumptions, so there's no public key infrastructure or CRS, etc. And for this talk, we'll consider the synchronous model of communication, where there is a man in the middle adversary that sees honest messages and then can arbitrarily change them and generate his own new messages. So he sees a message on the left, generates his own message on the right, and similarly, after seeing messages on the right, he generates his own messages for the left protocol. So now he has created two protocols on the left and the right, and suppose this is with reference to a commitment. then we will assume that both sides have unique identities or tags, and this is because we need some sort of differentiation between the left and the right. Otherwise, he could have just copied everything down from left to right. And we will be proving security whenever the left tag is not equal to the right tag, and they can both be adversarially chosen. And the kind of security we want to prove is that the value that the man in the middle commits to in the right execution should not be related to the value that was committed in the left execution. So there are two standard definitions. One is non-malleability with respect to commitment, and one is non-malleability with respect to decommitment or opening. So very roughly, non-malleable commitments with respect to commitment guarantee that on seeing a commitment to a message M, the man in the middle cannot commit to a related message. So in the real world, the man in the middle interacts with an honest committer who is committing to some input message M. The tags are different in both executions, and on the right, the man in the middle, let's say, generates a commitment to some other message M prime. In the ideal world, the same man in the middle interacts with some simulator that does not have access to the message of the honest committer and generates a new commitment to some message, let's say M double prime. Then what we'd like to say is that the distributions of M prime in the real world and M double prime in the ideal world are indistinguishable or close. So which intuitively means that whatever the man in the middle produced here after looking at a commitment to M can be produced by him even without looking at any commitment to the actual message. And the actual definition also considers the view of the man in the middle. So the value committed together with the entire view of the protocol should be indistinguishable in the real and ideal worlds. I've put some things under the rug here, but that is the essence of the definition. So non-malleability with respect to opening is a slightly weaker definition, where we only want to ensure that the man in the middle cannot open to related values. So it is okay for him to commit to related values as long as he cannot provide valid openings. So again, in the real world, the man in the middle sees a commitment, generates his own commitment, sees a decommitment and generates his own decommitment. And then in the ideal world, he again sees a commitment to, let's say, 0 and generates his own commitments, sees the decommitment and generates his corresponding decommitment. And what we roughly want is that the view of the man in the middle, together with the value that he was actually able to decommit to, should be indistinguishable between these worlds. Yes?
I mean, this is not in general weaker than.
This is weaker?
Comparable. No, you said that it's weaker than commitment.
Yes. It is.
I think it's not comparable. I mean, you would probably need it to equivocate on the left-hand side for.
So this is in general, I think, weaker. Maybe the definition that I am talking about is definitely weaker. Maybe there are some strengthenings of this that are not. So, so there's an issue here. The man in the middle gets to see the opening on the left. So a man in the middle might decide, whenever I see a decommitment to 0, I'm just going to abort all the time. So, but whenever I see a decommitment to some particular value, that's the only time I'll function. And this is a trivial man in the middle. Like, so to exclude such men in the middle, we are going to ignore all transcripts where the man in the middle decides to not decommit or decides to give a valid, invalid decommitment. So we'll replace this value right here with the wildcard value, which means that we are winning if he decides to not decommit properly. And again, very roughly, the definition says that his view together with the value decommitted, but ignoring these transcripts where he failed to give decommitments, is indistinguishable in the real and ideal worlds. So, okay, so let me tell you a little bit about prior work on this. The original paper by Dolev, Dwork and Naur gave an order log n round protocol for non-malleable commitments based on one-way functions. Then there has been a lot of work on improving the round complexity and the assumptions, and I won't go into details, but the current best protocols for non-malleable commitments have 3 rounds and are with respect to the stronger definition. And a result by Rafael Paz some years ago showed that at least 3 rounds are required if one wants black box reductions and non-malleability with respect to commitment. So the question we can ask is there any way to do any better than 3 rounds? And what we note is that the lower bound of Rafael Paz only holds for non-malleability with respect to commitment. So for non-malleability with respect to opening, can we do any better? So in this paper, we explore this question, and let me start by telling you the bad news, that actually if we wanted non-malleability with respect to opening in 2 rounds, even that is impossible with most natural reductions. And this natural reductions basically includes all reductions that we know so far, that we are aware of so far for non-malleability. So it looks like this is bad news, but the good thing is that this is only true for bidirectional messages. So non-malleability with respect to commitment is impossible. We show that even with respect to opening, it is impossible, but only if you restrict yourself to bidirectional messages. So what does that mean? A 2-round protocol for non-malleable commitments might look like this. The receiver sends the first message, and then the committer sends his own message. But if we change the direction of the first message to have the committer just send 2 messages one after the other, then we can show that it is indeed possible to get non-malleability with respect to opening in 2 rounds using 2 unidirectional messages from the committer and no interaction and no messages required from the receiver, a black box proof of security and with new techniques. But I can see that many of you are confused, and that is legit because why not just combine those 2 messages together into the same message and send it, right? But in this paper, we only study the synchronous model of communication, where the committer sends his first message, then the man in the middle is required to respond with his own first message. Then the committer sends the second message, and the man in the middle is required to respond with his second message. So the protocol proceeds in rounds, and this is useful in MPC settings, which are typically synchronous. And then there is the open. So our contributions, we give a 2-round non-malleable commitment with respect to opening, secure against all synchronous polynomial time adversaries, just making black box use of non-interactive statistically binding commitments, which can be based on injective one-way functions. And it has the best possible round complexity in the synchronous setting with natural black box proofs. So asynchronous, on the other hand, is impossible, just because those impossibility results extend. So, we also show that our non-malleable commitments have applications to round optimal secure computation, but I don't have time to go into that right now.
You're saying possible is only for natural, like for what you call natural?
Yes. So natural, again, without going into too much detail, it's basically covers all known reductions. So it's a very weird kind of reduction for which we don't know how to prove impossibilities.
When you say 2 rounds, the 2 rounds are only for the commitment phase. If you include the decommitment, it becomes 3 rounds?
Yeah. So if of course. Otherwise, it would just be a non-interactive commitment, right?
So did you try to design an unnatural one in 2 rounds?
We tried. It's really weird. So it's not clear what kind of an advantage that reduction would give. So. Okay, so techniques. So let me just give you the very basic idea. Suppose with a story, thanks to Yuval for the story actually. So suppose there's 2 students, Alice and Bob. The teacher really trusts Alice, but she doesn't trust Bob as much. So she gives Alice the option to answer with two answer sheets, and Bob only gets the option to submit 1 answer sheet. And so now, and Alice is instructed to fill in garbage values in one of the answer sheets and fill in the correct answers in the other. And Bob has absolutely no idea what the answers are. So if he's trying to cheat from Alice, he doesn't know which of the answer sheets to pick. So in the commitment setting, the honest committer, let's say his tag is 2 and is bigger than the man in the middle's tag. Let's just assume that for now. he gets to send 2 commitments, and he has to place his actual message in only one of these places, and he can just place a garbage value in the other. And the man in the middle gets to send just 1 commitment. So now it's pretty clear that the committer in the second round decides which is his actual message, whereas the man in the middle is already committed by then, which means that it is difficult for the man in the middle to copy the left value all the time. He can still copy in this super basic protocol with some probability, but we'll amplify the security. But this is at least half secure. So, and this actually also extends to bigger tags. For any tag that is in 1 to n, such that the left tag is greater than the right tag, we can just generalize this protocol to have the committer send tag many commitments and place his actual value at 1 position, so that the man in the middle who's trying to copy or do anything, he can have any arbitrary strategy, and it's actually possible to prove that just using the pigeonhole principle, that 2 left openings correspond to 1 right opening, which means that the left committer can open in 2 ways, and the right, the man in the middle on the right is stuck.
So this would this even hold if you didn't use commitments at all? Just send the m's in the clear, right? I mean, you still can't copy.
Yes, this would hold, but then maybe the man in the middle has extra advice about the message, and.
But it was like bits. You could do 0 and 1, and hide which one is your ashes. You could just.
Okay, maybe we can discuss that.
It won't be hiding.
Yeah, you do need hiding. But so.
No, if it's a bit, if you send all possible, the 0, 1 example, if you send all possible strings, it's hiding, like until.
But you'll get a small distributional advantage. You do need.
Yeah, you do need this, and just with bits. Okay, so with bits, you will get a one-sided secure scheme that way, but it's not clear. The proof of the 2-sided is going to get stuck if you try to do it completely informally, and it's not clear at all how to take it to strings. So. Okay, so so what we saw was for any tag in n such that the left was greater than the right, if you have more number of commitments on the left than on the right, then the man in the middle might fail in copying at least 1, and if you're lucky, it's that one where you placed your it's the one where you placed your message. And I'm not going into amplification issues right now, but that's the basic protocol. But what if the left was smaller than the right? In that case, the man in the middle might successfully copy everything, and he'll succeed all the time. But what we can do to avoid this is to set t to be equal to 2n minus your tag, and this ensures that 2n minus tag prime on the right is still smaller than 2n minus tag on the left, and now send 2n minus tag number of commitments. So then the man in the middle misses out, because if the left tag is smaller than the right tag, then 2n minus tag on the right is smaller than on the left. So this is a pretty standard technique in previous papers, to just add more rounds and commit to the message m using first 2n minus tag number of commitments and then using tag number of commitments, so that the man in the middle is going to fail in at least one of these situations, and set the bigger one first. So suppose he tries to copy, he misses out here. In the other situation, maybe he succeeds in the first case, but then he's going to miss out in the second case. So this is pretty standard in previous works, but the problem with this is that the number of rounds go up. So we want to do the same thing in just 2 rounds. So let's do it, let's send it together. So I send 4 commitments to the message and then 2n minus tag. So looks like the man in the middle can copy these 4. So what happens then is that the man in the middle can launch the following attack. He just copies those 4 on both the sets. So he just picks the smallest one and copies it, and this doesn't work anymore. But what we do to handle this is we show that plain secret sharing suffices to just handle this issue. And the way we modify the protocol is, let's secret share your message into A and B, and now use the first set to commit to A and then the second set to commit to B. And you can run it in parallel now. And note that if the man in the middle tries to copy now, he's going to have to mix things up, and that might not work out so well for him. So in this situation, maybe he copies like this, and things open up, and he thinks is 1. But there is a chance that the actual bit that was chosen to be opened on the left was sitting right there, which is what he copied onto his first set. So he can't open anything at all in his second set, and both things that he wants to open are in the first. So there is this different partitioning idea that suffices, and the man in the middle still loses with some probability. So to get full security, I don't have time to go into the details, but we just split the message, again using a XOR secret sharing, into many messages and commit to them using these basic blocks. So intuitively it feels like if he misses out even 1 share, he's going to lose, and with high probability he'll miss out 1. But the argument actually is not that simple, and we have to have a complex analysis, but it succeeds. So let me just end with some open questions. So many non-malleable commitments with polynomial hardness in 2 messages or even 3 messages is a very interesting question. Things become hard in the many setting, just because typically for many non-malleability, one uses interactive proofs, and it becomes hard to do such proofs with just 2 rounds and just 3 rounds. So this is an interesting question. And non-interactive non-malleability with respect to opening also has this natural black box reduction gap. So can we get non-interactive commitments, or can we extend the impossibility to rule them out? That would be interesting.